So I'm actually presenting a Steven paper today, Sheaving a Universal Construction for Semantic Compositionality. So I will start with a very quick overview of the paper itself, try to summarize it in one sentence. And essentially, this paper proposes sheaving as a category tiered framework to explain semantic compositionality by systematically integrating local information into global coherent meaning using topological structure. And hopefully, during my presentation, these words will become more clear. So let's start with semantic compositionality. Semantic compositionality is how the meaning of complex entities is derived from the part that constitutes those entities. And as the paper mentioned, some form of compositionality is supposed to explain concomitant cognitive capacities, such as the systematicity of language and thought, right? But this historically has been a problem for the traditional approaches in cognitive sciences. And so, for example, the two main approaches, like the classical theories or symbolic approach, and connectionist theories or neural network approach. For the classical theory, we have that the idea or like the proposed explanation is that the cognitive capacity are systematically related due to shared syntactic structures, but these relies a lot on assumptions, and there is no formal explanation for that. And the source of the structure is also unclear, and it's not derived from the principle of the theory itself. And therefore, it has been easy historically to provide counterexample, and for those counterexample, each time you need ad hoc adjustment. So these usually are characteristics of non-very solid explanatory approach. On the other side, we have connectionist theories or neural network approach, where cognition is represented through patterns of activation across distributed networks, as the name suggests. And in this context, systematicity is supposed to arise from shared neural activation and vector operation, for example, tensor product. And this approach has been good maybe to explain the how. Actually, I should say that the weak point of both approaches are common to both. So in both cases, like there is or there can be an explanation of the how, but the explanation of the why, which in my opinion is the real explanation, is weak or lacking generally. So systematicity in this sense has been a long-standing issue for cognitive science. So in this paper, as I mentioned, category theory is used as a tool to formalize compositionality. One key idea of category theory is universal construction, which capture systematically how certain capacities are related. And I think there is a great example in this paper, which personally I find very useful, and I really recommend everyone to read the paper, to read this example specifically, which I also use in my presentation, and is the example of a deck of cards and playing cards. And we can see very easily through this example how different properties of the cards, so for example, the suit and the rank, can be systematically combined using category theoretic tools. And I found this extremely refreshing because usually category theory is very abstract, it's considered very abstract and complex topic, but through cards, in my opinion, it does become quite concrete and not complex at all because of the nature of the exam. Yeah, and And then we look into universal morphism, which generalize relations between objects in a category. And also, I'll go a little bit more into the details, and which can provide an explanation on how these cognitive capacities are connected. Okay, so we'll consider like a deck of cards. We have two main properties, rank, so the number of the card or the face of the figure, and then suit, so heart, diamonds, and I'm sorry, I don't know the English name for the
clubs and spades. Club
yeah,
and spade.
Clubs and spades. Thank you very much. Okay, so here we see very simply how one card is given by the Cartesian product of those two sets, right? So for example, the Cartesian product of, sorry, the set of cards is given by the Cartesian product of the set of cards and the set of suit. So in the set of cards, we have a series of 52 ordered couples, which are, for example, 2 and hearts, 2 and spades, 2 and diamonds, and 2 and clubs, and so on and so forth, until we have all 52 cards. But we also have certain functions that, given a card, so for example, a rank function or RK function, that given a card, it gives you back the rank of that card. And again, this is extremely intuitive when it comes to card, but I think it's very useful to use intuitive example in this context. And similarly, we have the ST function that given a card, so ace of hearts, it gives you the suit of that card, so heart. And so we can go back to the paper, and category theory starts with the formal concept of a category, which consists of a collection of entities called objects, and a collection of relations between objects called morphism, and an operation that takes two morphisms and returns a morphism called composition. And so just for graphic purposes, in this case, we have rank, suit, and card that are objects, and RKST that are morphisms. Okay, so again, we look now into the second aspect, so the composition of functions. And again, we can consider a deck of cards as a mapping of each face. So for example, yes, we have a function that given the card, so for example, the Queen of Hearts, it gives you the ordered pair of the Queen and the Heart. And this kind of mapping is given by a yeah. Hello?
Yep.
Oh,
I can
okay.
see you.
Sorry. So and this I was saying this kind of mapping from faces to ranks and from faces to suit are given by composition. So we take, for example, face rank function, which is a composition between RK and card, and face suit, which is ST and composed card, respectively. So, for example, face rank, we have the Queen of Hearts, and we got the Queen. We got the Queen, and because of course the face of the Queen of Hearts is the Queen, and essentially this is a category theoretic model of playing cards. Now we can add a layer, so to say, and taking into consideration functors, which is a way to indexing objects and morphisms. So, for example, we can have the product pointers that construct the set of cards from the set of rank and suit. So so we start with the, as we did before, we start with the rank, we start with the suit, and we obtain the set of the entire deck. Then again, we can add, so to say, a layer, and we have two functors. When we have two functors, they can be related by something called a natural transformation. And then there will be, or there can be, an optimal transformation, which means essentially the one that is most efficient, and that we call a universal morphism. So again, as an example, we can take the set of cards, their rank, and their suit in the universal morphism card RS, where RS is the sorry, did I write this correctly? Yeah. 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 I'm sorry, I need to check. Steven, can I ask you, is this correct, right?
Yep, that's correct. Yep. So it's
okay.
It's a pair of arrows.
Yeah. Okay, sorry, I just wanted to be sure. Okay, and so this is the transformation that is efficient in the sense that there are no more and no fewer mappings needed that are needed to retrieve the rank and the suit of every card starting from the deck. Okay, now we take into account sheaving, which is essentially like starting from this category, starting from the category theory approach. We have sheaving as the method that systematically combines local information into a globally coherent system. And in this, we look at a press-sheaf first, which is something that assigns data to region of a topological space, and a sheaf that actually is a press-sheaf that satisfies additional conditions, such as that the data is consistent across all overlapping regions. And then the paper provides 3 examples that pertain to the cognitive sciences, such as visual feature binding, depth perception, and playing cards. I think I'm actually probably well above my 5-minute limit. So very quickly, we can just look into pre-sheaves or sheaves as functor and sheaving as the natural transformation. And in this sense, sheaving works like a natural joint in a database when we combine information from different tables. And again, we can consider this example of the list of the address of people and the medical record of those people, and thanks to this list, we can find where certain medication will be. And similarly, sheaving bridges gaps in knowledge by merging local data into a coherent whole, using this topological relationship to give meaning. So maybe we can skip this. And so semantic compositionality involves systematically connecting representation with their corresponding entities. Sheaf theory explain this by attaching data to a topological space where the shape or topology conveys the meaning. The structure of the space is preserved either locally through a pre-sheaf or globally through a sheaf. And this process of sheaving allows for inferring broader relationship by merging local information coherently. by gluing together overlapping data, Sheaving creates and unifies a systematic understanding of complex entities. And yeah, so here there are some potential question or things that maybe could be interesting to discuss. First of all, like if like this, to me, this approach Sheaving seems also extremely pertinent to the frame problem also discussed in cognitive science. And I was wondering, Steven, if like what you think about that.
Mhm.
And then yeah, essentially my biggest question is like the general overall theoretical structure seems indeed very powerful, because when you have a structure, you don't need to reconstruct, so to say, the meaning from every single component, but you can simply move across the structure itself, right? But the question that is still not very clear to me is how easy, in a sense, or difficult is to applying this kind of modeling to real world data or aspects of cognition. And as you know, that we're trying to look into that for to consider the relationship between narrow and broad qualia. So of course, this is very interesting for me. And thank you, everybody. I hope this. Sorry, I went maybe a little bit over the time.
Excellent. Thank you, Francesco. Let's open the discussion. Please go first. And if no one has any, okay, we have Kusano-san, and then we have Misa. Okay, Kusano-san.
Thank you for the presentation. Before the discussion, I want to ask about the layer. So I couldn't understand what the layer actually, because I just started to study category theory. So I'm the beginner of that. So what was the layer in the, you said the Trump example? What the layer means in the example of the Trump card game?
Yeah. Sorry, which example?
Card deck.
Yeah. So
What was the layer?
Okay, the crucial question seems to be, what do you mean by layer?
Yeah.
Either, yes. Actually, I'm a bit puzzled myself. So maybe there was a miscommunication there. I'm not sure what layer is supposed to mean. And I didn't actually. Yeah. Maybe could you rephrase the question possibly, Kusama-san?
I was reading the. Okay, I will check again. So can I take more time to check? I'm sorry.
Yeah, sure. Actually, while we're there, I will search my paper for the word layer and see what. Actually, I couldn't find the word layer in my paper, so I'm not sure.
Okay, I will check. I'm sorry.
It's okay. Okay. Well, Kusano-san is checking that. Misa, would you like to ask a question?
Thank you very much for the presentation, Mr. Francesco.
Just Francesco, please.
Yeah. I have a question to both of you, Stevens and Mr. Steven and Mr. Francesco. So you said that the Sheaf method or the Sheaf model theory is model that maps meanings to in the topological space, meanings to shapes, probably, I think. Or is it, am I correct?
Well, I think Steven should, maybe I can say my understanding is that the meaning is given by the shift as a way that systematically relates the information in the topological space. But of course, I think Steven should reply to your question because.
Yeah. So
that's pretty close. In the paper, yeah, the topological space is, or the structure of the topological space is the meaning. Importantly, sheaves, there's a reverse map as well called a fiber bundle, which is sort of what's called so instead of going from the topological space to the data, you can also go in the other direction from the data back to the topological space, and that's called a fiber bundle. And those two categories are very closely related. So
is there any assumption that those data don't have any meaning? Because you need to map those data to in the topological space.
Yes, so the data themselves will be just like the perception of that particular concept, for example. So you might think that the structure of the concept may be the topological space, and then the instantiations of that concept are the particular instances, the data sitting on top.
Oh.
And maybe getting back to Kusuno-san's question, the layer, in one sense, a good way to think about sheaves is like a database where the topological space is the header of the database and the rows of the database are your data. And so if you think of the rows as layering on top of the topological space, there's a sense there in which you have multiple instances with the same underlying structure. Okay.
So the intention of this model is to, like in your paper, you said there is people in cognitive scientists, they don't understand the meaning of symbolic, and the difference between symbolic and non-symbolic semantic or mechanism. There is a duality between those two. So I would like to know if this model is trying to understand or to mostly represent symbolic meaning or symbolic semantic. Also.
Okay, that's a good question. It's a little bit, there's another paper getting onto this issue, but the crucial point, or a way to think about this is what kind of topological space that you're working with. So if the points that you're working with are discrete points, like the cards example, then you can think of that more like a symbolic representation. But not all other topological spaces are built on infinite sets. Like, for example, the set of real numbers itself has a topological space. And that acts more like a non-symbolic situation. And so the point about working with sheaves and pre-sheaves and topology generally is you can cover both within the same general framework. Okay, and importantly, you can also work between the two. Okay. And we haven't heard from Chihiro-san. Would you like to ask a question or comment?
Maybe Kusano-san, don't you have other question?
Yes, I found it was a sieve because I tried to retranslate something that was once translated in Japanese. It was a sieve. It's okay, thank you.
Okay.
If you have any questions, Chihiro-san, you can take them.
So because I am a very beginner of category theory, so my understanding is very shallow, especially for sheaving. So, but maybe my question is related to Mesa's question one. So how this approach is useful to interpret the complicated world or composed of a symbolic and some quantity and how we can connect if this theory enables connecting symbolic, how this theory can connect symbolic world and quantity world.
Okay. Very good. I think this also relates to Francesco's question about how difficult it is to apply sheaf theory. So I'll try to answer both questions at once. In the general, there are several ways. The sheaf theory involves quite a lot of arrows, and so there are multiple ways of doing this. One way, alluding to the previous point about symbolic versus subsymbolic, you can have arrows or you can have maps between topological spaces. And so that changes the structure of the topology. Okay, that's one way. That probably answers Chiho-san's question more in one sense. Now, to answer Francesco's question in another sense, the data also can change. So in the simple examples in the paper, we just used say discrete data like the ranks and the suit. But you can also do something like Michael Robinson did in the summer school and use numerical data. So if you can, for example, probability sheaves where the numbers are real numbers and so forth, and that gives you more quantitative sense in which the data are attached to the topological space. So there's quite a bit of variation that's possible. The paper just gives you three very, very simple examples. In fact, the third example is probably closer in line with the quantitative example because we're trying to triangulate the location. That's probably more closer to Michael, although Michael Robinson does much more sophisticated examples than what I did in my paper. So that's one way of doing it. And actually, sheaf theory is, the sheaves can be extended in a variety of directions. Firstly, by changing the topological space. Secondly, by changing the data on which the topological space sits. So the very basic examples are the set valued sheaves, but we can have other kinds of structures in such that the rows between the data, the relations between the rows are also expressed as well, and then as either discrete values or continuous values like real numbers, and we can also have other constructions as well, relations between the sheaves and the categories of sheaves and so forth. So, and also, one thing that the paper doesn't really pick up on, but Michael picked up on in his talk, is that the topological spaces I talked about there are very simple topological spaces. It's what you see in general topology, but other things, more complicated structures like graphs, which you'd see in language, are also construed as topological spaces. So there's a wide variety of things that you can do, and things that Michael talked about, simpler shear or complexes and so forth, have much more structure than the simple cases that I mentioned in the paper. So yeah, so the short answer is yes, there's a variety of ways of doing that, but knowing what way to approach it really takes quite a bit of experience in working around intuitions with the different kinds of things, as is typically the case when you take a formal approach. We're right at 3 o'clock. Let's have one more question before we move on to.
Can I ask it's okay.
Yes. Go ahead, or both of you go ahead.
Quick question. So, if you wanted to think about simplifying of the meaning of a language, would you take each object as each word and infer the whole by sheaving? Is it right understanding?
Do you mean a word within a sentence or just a single word by itself?
I think single word.
Word would have some semantic features, I suppose, and then the question would be how to organize those semantic features. I don't have an immediate answer.
I'm confused. Just a 90 question, so I'm sorry to confusing.
No, it's interesting question. You can, if you think if you think of words as residing in some vector space, then the vector spaces themselves are quite closely related to sheaves. For example, each dimension, for example, constitutes can be regarded as a. Oh, there's several ways of doing it, but the most simplest way is to take each dimension as a point in the vector space, and then the feature that word, the feature values of that word are the data that sit on top of that space. Okay, and Lisa, would you like to ask one quick question before we move on?
I was just wondering, like, about the computational aspect of implementing this model, because each word has already a context, it already have a meaning. So it's already a lot of information for one word. So I was thinking that mapping from topological space to meaning itself is quite difficult, will be quite challenging. And I think a meaning itself, I don't know what is the nature of this data, what could be the nature of this data, and the nature of this meaning itself, and what could be represented, like what could be a formal representation of this meaning itself, like would it be A, B, C, or would it be a word? Would it be a sound? Something like that. I'm quite unsure about the nature of the meaning, and I think it will complexify the model itself if we implement it.
Yes, a very good question, and one that Michael Robinson would be the best person to answer, because he has implemented, or his group has implemented these computational methods for this kind of stuff. Okay, sorry to cut the answers short. Thank you very much, Francesco, for your presentation.
Thank you. I hope I made justice to your paper. But
Very good.
I found it extremely useful. Thank you so much.
Well, thank you for presenting it. Okay, so let's move on to Chihiro and